just kind of a refresher, we said that there's this thing called mechanism, which basically is a series of elementary steps behind the scenes that occur. They all add up to an overall reaction of interest. And then we talked about there is the very important elementary step called the rate determining step. It's the slowest. And so you kind of focus on that. You can use molecularity if it's an elementary step to understand reaction orders, but only if it's an elementary step. You can use molecularity. You can knock out a rate law expression with regard to that elementary step, that slow one. If it matches your observed rate law, then you're done. You are consistent with the mechanism. Okay, the mechanism is consistent with what's observed. Now this one's a little bit different. Here's the twist in this one. It's something we talked about before. We said that behind the scenes we're going to have a fast step and then we're going to have a slow second step. So here in a minute we're going to focus on that slow second step, okay, because that's rate determinant. So it kind of starts out the same. We have two particles of NO react with one particle of O2 to form two NOBr. So that's your reaction of interest. Let's say that the observed rate law expression looks like this, where rate for this is equal to the rate law constant K times NO raised to the second power times molar concentration of Br2 raised to the first power. Now right off the bat you might be like, well, look, I can use molecularity up here and I got NO as second order, Br2 as first order. No, you can't do that. That's a reaction of interest. You cannot use molecularity. If it's an elementary step, yes. Reaction of interest, no. Nice try. The other problem with using the molecularity of the 2NO plus 1 Br2 is you're back to a trimolecular. The odds of getting, it's like herding cats. The odds of getting 3 pieces together at the right place are not very good. Elementary steps are bimolecular or unimolecular. So those two things. So this is a proposed mechanism. These are our 2 elementary steps. Aren't they adorable? If we add them up, okay, notice that the NOBr2 cancels. Okay, so then we get the 2NOBr2 goes to form 2NO plus 1 Br2 goes to form 2NOBr. Okay, so one check on your mechanism is, do my elementary steps give my reaction of interest? The answer is yes. Now, the catch here is, starts with the letter I. What is this NOBr2? It is an intermediate. That's the catch. Intermediate. An intermediate is something that basically is annihilated by all the elementary steps when we look at it. The other thing is the intermediate does not appear in your overall reaction of interest on either the reactant or the product side. The problem with that then is you're going to see on the next slide is we're going to focus on the slow elementary step just like we did on Friday. We're going to use molecularity. We're going to call that first order and that first order. That's fine. Okay? First order, first order. The problem is we can't stop there because we have a rate law expression that has an intermediate in it. If this is the case, I'm going to show you how to fix it. Okay? This is not acceptable since it has an intermediate in it. If this happens to you, probably if this is your slow step, has intermediate in the reactant side, because you use your reactants, the molecular reactants to get your rate law expression. If you look before it, you're probably going to have a fast equilibrium elementary step. And I'll show you how you can use that to your advantage. So we're going to turn, in order to get out of this bind, we're going to look at elementary step number 1. I'm going to show you how to focus on that equilibrium to massage out something to substitute your intermediate for, something tangible to get rid of your intermediate. So here we go. Here was the one that we kind of blew off because it's fast. but it has our intermediate here. Now, we're going to be talking in Unit 3, don't miss lecture Friday, because I'm only going to say it once. In Friday's lecture, we're going to start talking about chemical equilibria. So equilibria, I think we talked about before, will have an arrow going from left to right, and it'll have an arrow going from right back to left again. Goes in the forward direction and the reverse direction. The cool thing about equilibria, yes, that's plural, equilibrium is one. Anyway, is that the rate in the forward direction, if it's established, then how much it goes forward, or the rate at which it goes forward, is equal to the rate at which it goes backwards. Okay? Well, that's awesome. Since it's an elementary step, we can use molecularity. So here we go. In the forward direction, we're going to actually use the rate law constant K1. In the reverse direction, we're going to go K negative 1. Using molecularity, in the forward direction, the rate is equal to K1 times more concentration of NO times more concentration of Br2. When it goes backward, notice now my reactant is NOBr2. So in the reverse direction, okay, the rate law expression, rate is equal to K minus 1. These are two different rate law constants. Using molecularity, NOBr2 raised to the first power. All right. Well, we said that if it's at equilibrium, the rate in the forward direction is equal to the rate in the reverse direction. So the next thing I'm going to do is to set these two quantities equal to each other because it's at equilibrium. At equilibrium, the rate in the forward direction is equal to the rate in the reverse direction. K1, more concentration of NO, more concentration of Br2 is equal to K negative 1, more concentration of your intermediate. And we're almost there. I told you we're using this to get something that we can substitute in. I'm going to rearrange this on the next slide, just basically getting NOBr2 by itself, and then I'm going to plug it into my rate law expression using my second elementary step, the one that was the rate determinant one. So here we go, just getting NOBr2 by itself because that's the intermediate. That's the thing we want to get rid of. From earlier, when we looked at the second elementary step, this was the rate law expression we came up with, the rate determinant step. This is where we want the substitution to occur. So basically, we just take this quantity and plug it in there. And it looks like this. It looks kind of weird with all those K's, okay? Rate law constant K2 times rate law constant K1 divided by rate law constant K negative 1. Here in a minute, I'm going to take all those K's and make them one big K. But the other thing we have is the molar concentration of NO, molar concentration of Br2, molar concentration of NO. Okay? So of course, we're going to combine these NOs to make it NO raised to the second power. So if we make this ball of K, or these K's all 1K, combine our NOs, we get this, which hopefully this rings a bell, because this was the observed rate law expression for the reaction of interest. That's how verifying mechanisms work. If you can look at your mechanism, focus on the rate determining step. In this case, we had to get rid of an intermediate by using the equilibrium before it. Okay. I come up with the observed rate law. You're there. Okay. Okay. Well, I kind of finish up by looking at catalysts, and I think I meant to mention before, a catalyst is something that will make the reaction of interest occur more quickly, and it does it, this kind of blows my mind, by actually creating an alternate universe, by creating an alternate path behind the scenes, an alternate mechanism. And we're going to see these alternate paths when we look at energy diagrams. So look for, on these energy diagrams, look for the activation energy to be lower for these catalyzed reactions with an alternate path versus for the original one without with the uncatalyzed reaction. Okay, so blue is catalyzed, red is uncatalyzed. We've talked about so would this be endo or exothermic? Endo, yep, this one's endothermic. But they both have energy barriers to proceed from reactants to products. So you can see the blue has a less energy barrier than the red does. And I think we talked about this, yeah. Can you see where actually, to me, the red, I just see one hump. So that's probably it's probably an elementary reaction. The blue, I see two humps. Each hump is a different elementary step. Here's one for you, and I think I was just tired when I was getting ready for today's lecture last night, but this is taking formic acid and breaking it down from carbon dioxide and water. This is uncatalyzed, okay, and if you look at it a few times, I was like, what? So basically, well, anyway, that carbon sticks with that oxygen, and then this water breaks off. Looks pretty straightforward, but wait, it can be even better. If you go ahead and this little H plus in there, we're going to be talking more about that. And if you have acidic conditions, you have H pluses running around galore. Okay, it's just an acidic condition, a hydrogen ion. So that's going to be our catalyst, and see what part it plays. This is kind of fun. Let me grab my pen, because yeah, it kind of made my eyes go blurry. So basically, this guy, to me, he looks like he sticks on, let's see if I compare these two. To me, where he's going is right here, okay? And then we have kind of a break apart and a break apart. And then, of course, this is going to become our carbon monoxide, so it'll kick off that hydrogen ion again, or proton again. Okay, one of the things about catalysts is they are not consumed in the reaction. They just kind of help facilitate it. So you can kind of see these different little elementary steps. Is that adorable or what? But the point here is that the activation energy is less in the catalyzed versus with the catalyst and without the catalyst. So of course you guys hopefully tell me the pink here is without a catalyst, the blue is with a catalyst. So you're going to look for the kind of the lower one. This one doesn't look as dramatic, and to me, both both mechanisms to me look like they are maybe unimolecular, or they occur in just a single unimolecular. Sorry, they are elementary reactions occur in single elementary step. But again, you look for the lower activation energy, and that is where a catalyst is being used. Now, you told me the other one was endothermic. This one looks exothermic because your energy of your products less than the energy of your reactants. All right. So these will be due on Wednesday. Which everybody's going to come. Nobody's going to be sick. Honestly, all kidding aside, if you are sick, stay home. So So let's take a look, kind of finishing things up. Part 7, we started out this unit talking about reaction orders. And that's the dependency of the rate of the concentration of the reactants. Raise the first order, raise the second order, raise the zero order. But actually reaction orders can be negative, but reaction orders can also be fractions. And I want to kind of talk you through what would that look like. How can you get a reaction order of 1/2 or 3/2? Okay, of your overall reaction order, considering your reaction mechanism that happens behind the scenes. So let's consider this, where I have 3 elementary steps. Okay, I'm going to add them all up. Do you guys see any intermediates there? I'm liking B, yeah. And D, did you say?
And that because they're not in the end?
Right.
Okay.
They're not in the end. I knew they wouldn't be in the end because I had the same number on either sides of all of the columns of reactions and products. Yep. So B and D are intermediates. So yep, we got an A plus C going to form E. So which one are we going to come up with or use to get our the ball rolling with regard to the rate? Which elementary step?
2.
2. Yep. We're going to start with 2. And actually, right off the bat, can you see where we're going to have an issue with 2? Because we have an intermediate, B. So we can actually, we're going to get the ball rolling there, and then we're going to have to use R for elementary step 1 to get rid of B. Yep. So elementary step 2 is the slow one. We use molecularity because it's an elementary step. It's first order with regard to B and C. So we have rate 2 is equal to K2 times B raised to the first power times C raised to the first power. But like I said, the problem is that you guys told me that B is an intermediate. And so we can't just say, hey, this is the slow step. So this is going to be our overall rate law expression because you can't stop there. We've got to fix it. So if we look at the first elementary step, kind of do what we did before, we're going to have the rate in the forward direction is equal to the rate in the reverse direction. The rate in the forward direction, it will just be K1 times the molar concentration of A. The rate in the reverse direction will be K minus 1 times the molar concentration of B raised to the second power. When we go ahead and set these two quantities equal, and we solve for our intermediate. Now, there's where life gets a little interesting. There's actually where our half order is going to enter in, because we're going to end up taking the square root of a quantity to get to just one of these, because we got B squared there. So if we move K1 over, you got K negative 1 over, you have K divided by K negative 1 times A, molar concentration A raised to the first power. To get B by itself, you have to take that quantity raised to the 1/2 power. So what we did before then, we're going to do it again. We're going to take this quantity and substitute it into the rate law expression we got from the second elementary step. So if we take this quantity and slide it right there, combine our K's, okay, you end up with this, where the rate is equal to rate law constant K, and K behind the scenes is really K2 times quantity K1 over K minus 1 raised to the 1/2 power. It's all in our K. Molar concentration of A raised to the 1/2 power times the molar concentration of C. So that's how you can actually get a half reaction order. Let's do another one. See how that was 1/2. Let's see if we get 3/2. It'd be a similar sort of thing.
You don't care about the product.
Don't care about the product in these. Only time you do is if you're doing the fast equilibrium to get rid of an intermediate. Yep. So let's see, any intermediates here? I'm liking B. Anything else? I don't think so. So you got 2A plus C going to form D plus E. So which one are we going to focus on to get the ball rolling with regard to the rate law expression of the reaction difference? Elementary step 2. Yep. So elementary step 2, since it's the elementary step, we can use molecularity. Rate 2 then will be equal to K2 times molar concentration of B raised to the first power times molar concentration of A raised to the first power. Doesn't that look funny to you how, I go DA instead of AB? So B is a intermediate, you gotta get rid of it. So we're gonna turn our attention to elementary step 1. The rate in the forward direction is equal to the rate in the reverse direction. In the forward direction, we have K1 times the molar concentration of A raised to the first power. In the reverse direction, again, we have K minus 1 times the molar concentration of B raised to the second power using molecularity. Go ahead, it's at equilibrium. We set these two rates equal to each other. K1 is equal to molar concentration of A. K1 molar concentration of A raised to the first power is equal to K minus 1 molar concentration of B squared. Getting B by itself, it looks like this again. Molar concentration of B is the square root of quantity K over K minus 1 times the molar concentration of A. And then we're going to go ahead and take that and substitute it back into our rate determining step. And this is where actually, can you see what's going to happen? Is if you take A to the 1/2 times A to the first power, you get it add the powers, and you get 1/2 plus 1 or 3/2. That's where your A to the 3/2 power will come from. We're going to combine our K's. And it looks like this. QED. So we spent a fair bit of time working around reaction orders of 0, first, second. Okay. But these are out there too. I'm not going to work this one. But let's see, what intermediates do we have? B. Oh, you're fast. D. Yep, B and D are intermediates. Again, I don't think I have the full thing, but can you see where we would focus on the second elementary step again, because it's slow. We have an intermediate there, okay? And we're going to actually end up with the same as we ended up with before. The same pattern. And there you go. We've got 2 sets of homework that I'll do one more thing. It'll be good for you. Be sure, hopefully you're working on those problems in the end of your units. Should help you for the test. Because the little bit that I'm going to do Wednesday is not enough to get you ready for Thursday's test. She says something. And be warned, I think Wednesday we're going to go around the room.